So this video is about mass spectrometry. This is a technique that allows us to actually weigh a molecule. So take a molecule and figure out its mass. Now, we don't have any scales that are sensitive enough to be able to detect the mass of a single molecule. So instead we use an instrument called a mass spectrometer. And this is a schematic of how the mass spectrometer works. So the sample enters at the left-hand side here, and the sample is in the gas phase. The sample is then passed through an electron beam. So the molecule is bombarded with electrons. And there's a little equation down here that shows what happens when your molecule is bombarded with electrons. So there's our molecule, M. It's hit by an electron, and that actually has the effect of knocking out another electron out of our original molecule. And so what we're left with is a molecule is now positively charged, and it's a radical. So now we've turned our molecule of interest into an ion. So then that ion then travels through the mass spectrometer and it passes through a magnetic field. And then the path is bent because of that magnetic field, because our molecule is now charged. Now, if the molecule has a low molecular weight, if it's only a small molecule, it will be bent a long way. Whereas if the molecular weight is higher, then it won't get bent so much and it will travel on a different path. Finally, our ion is going to land on this collecting screen and be detected. And the position that our ion lands on this screen is going to depend on the molecular weight of our sample. And so that's how we figure out what's the mass of our sample. So this is what an example of what an actual mass spectrum looks like. So the molecule that we're analysing here is hexane. So this C6H14. There's hexane there. And this is what the spectrum looks like. So on the x-axis is mass to charge ratio. And if we just assume that the charge is always +1, then this x-axis just means molecular weight. And then on the y-axis is abundance. So how abundant the signal is at a particular mass value. So the first thing you do when you look at a mass spectrum is you look over on the right-hand side to see what's the molecular ion. And in this case, the molecular ion appears at mass 86. So you remember the molecular ion is what you get if your molecule is bombarded with electrons. An electron gets knocked out of the molecule and we get turned into this molecular ion here. So that value of 86 is exactly what you would expect for a compound that has the formula C6H14. So here's another example. Now we're looking at a different analyte, cyclohexane. So in this case, you look at the molecular ion, and there it is at 84. And that's exactly what you would expect for a compound that has a formula C6H12. So there's a few other things to note with these two mass spectra. First of all, there's a bunch of other signals here at lower mass values. And that's because under the extreme conditions of electron bombardment, often the molecule will actually break up into fragments. And so you can see those lower molecular weight fragments appearing also. So that's why the one on the right-hand side is the most interesting one, because that's the occasion where the molecule survives intact through to the mass analyzer. So the fragmentation pattern is one thing to note. Another thing to note about this, if you look carefully at the molecular ion here, there's a little signal right there, just to the right of it. So what is that little signal just to the right, at M+1? There it is over here as well. There's another small signal just to the right of the molecular ion. Well, that small signal actually comes from the carbon-13 isotope in the sample. So you imagine a molecule of hexane. The vast majority of the hexane molecules will contain, all of the carbon atoms will be carbon-12. But occasionally, a molecule of hexane will come along where one of the carbon atoms, by chance, is carbon-13. So that molecule will have a different mass. And so for those occasional times, that's why you see a little signal here to the right at M+1. So this idea of isotope patterns is actually really valuable in mass spectrometry. So we can get a lot of info out of the isotope patterns. So hydrogen, not so useful in terms of isotope patterns, because almost 100% of the hydrogen natural abundance is hydrogen 1. It gets more interesting though with carbon, because then you've got a 1% abundance of carbon-13, which means that starts to become meaningful in the mass spec and we can detect that difference. It's even more obvious if you have chlorine in your molecule, because then you have a 3-to-1 ratio of chlorine-35 and chlorine-37. So if you have a mass spectrum that shows a molecular ion differing by 2 units in a ratio of 3 to 1, that's really good evidence that you have a chlorine in your molecule. And similarly with bromine, that's got two isotopes of 79 and 81 in equal abundance. So if your molecule contains a bromine, that's really obvious in mass spec as well, because that will give two signals of equal intensity separated by two mass units. So here's a real-world example of where mass spec can be used. It's used in doping detection. So this is a picture of Marion Jones. She won 5 gold medals in track and field at the Sydney Olympics. She subsequently admitted using this steroid, so she was doping. And she was subsequently stripped of all her medals. So the way she was caught out was through mass spectrometry. So it turns out that in the human body, we're naturally producing steroids like this. And in the human body, naturally, the steroids that we make naturally contain about 98.9% carbon-12 and 1.1% carbon-13. That's the natural abundance of carbon-12 and carbon-13 in our body. If you're doping, you're taking steroids that are likely originally from plant material, and from plant material, the isotope pattern is slightly different. So in plants, the amount of carbon-13 is more like 1%. And so mass spectrometry can tell the difference. Mass spec is sensitive enough to be able to tell the ratio between carbon-12 and carbon-13 for a particular analyte and figure out if it's a natural abundance or a non-natural abundance. And that evidence was enough to strip Marion Jones of all her gold medals.